Hello everyone. I hope that all of you are fine. Welcome to another session of Robotics Lab. In the previous lab, we learned that how we can find a shortest path in the graph using Dijkstra's algorithm. If you have already covered it, then you remember that we have created some nodes there, and then we defined the start and our goal node, and then there was an adjacency matrix, and there was also a cost matrix. We made these matrices because we needed them for our Dijkstra's function to find the shortest path. So what were the inputs of this Dijkstra's algorithm? There was adjacency matrix, cost matrix, start and goal node. And then Dijkstra's algorithm gave us the path and the distance or the cost. Let's see today. In today's lab, we shall use Dijkstra's algorithm to find shortest path in a grid, or you can say an occupancy grid map. So let's open a new editor, and first we need to save it. Okay, let's name it grid Dijkstra. Okay, let's save this one, and from here we can now start. So the first thing is we have to make a grid now, and for the grid we need to define first the nodes. So let's see that. This is our grid here. Let's say we make 4x4 grid. And 1, 2, 1, 2, 3, 4, and also we have to make columns also. So this is our 4x4 grid we have, and so here we can write here 1, 2, 3, 4, 1, 2, 3, 4. As you can see that the distance between each neighboring cell is 1. For example, this is our, let's say, the first node, and the second node we have a distance of 1, and we are only considering here the 4 connectivity. So each node is only connected to vertically or horizontally. There is no diagonal connection between the nodes. So let's also number the nodes. Let's say we have node, this is node 1, 2, oh, this is not working good. So I think I should disable it into shape, and yes, now it should work. So this is no way. I think that's a disadvantage of using automatic figures. So let's see that just by the visualization. So this will be our node number 1, and node 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have total 16 cells, and you can say we have 16 nodes also. Okay. So what we do here, we just convert this this grid into the graph, and let's define some of the how we can do that. Let's say we have here, this is node number 1 here, and let's say we have obstacle here. I forgot to mention here. Let's say here this is filled with obstacle. This is strange. My manual method was much better. So, okay, let's say that 1, 2, 3, 4, 5, 6, 7. Let's say that node number 6 and 7, 6, 7, they are filled with obstacles. Okay. So, starting from node number 1, this is our node number 1. We now represent our grid in a graph form. Okay. And remember that this is a binary grid, okay, binary occupancy grid. So there can be either obstacle or no obstacle. And yeah, so let's convert it into a graph. How we can do that? So this is the first node here, that this cell number first. We say this is node 1, and how many neighbors it has? 1 and 2, okay. And we connect it with, okay, first we make the nodes only. 1, 2, 3, 4. Then we have here 5, 6, 7, 8. Then we have 9, 10, 11, 12 here. And then we have 13, 14, 15, 16. So we have made here 16 nodes, and now we shall connect them with edges. So this is important here, because this connectivity of edges, it will be we have to convert it into our adjacency matrix in Matlab. Okay. So node number 1, this is connected to node number 5 and node number 2 here. 1, 2, 3, 4, 5. Okay. So let's connect it with node number 2 and node number 5. And similarly, node number 2, when we look at node number 2, it is connected with node number 3. And here we said we have obstacle here in these two nodes. Okay. So node number 2, it is connected with node number 3, but there is no connection between node number 2 and node number 6. And similarly, node number 3, it is connected with node number 4, but since we have obstacle here, so there is no connectivity to node number 7. And then we go to node number 5, it is connected to node number 5, 6, 7, 8, 9. It is connected to node number 9 here, but there is no connectivity to node number 6 because it is there is an obstacle here. And then we have node number 6 and 7, they are blocked. So we say that there is no connectivity to any nodes. And then we have node number 8, which is connected to node number 4 and also node number 9, 10, 11, 12. Yeah, node number 12 here. And then we have node number 9 is connected to 10, 11, 12, node number 13, and node number 10 also. Similarly, node number 10 is connected to node number 11 and node number 14. And or let's make obstacle here also. Yeah, let's make here also, let's say we have here also obstacles to 6, 7, 10, 11. So we have obstacles at, let's see, obstacles at node number 7, 6, 7, 6, 7, and then we have 10 and 11. Okay, so they are not connected, and the other nodes, they are connected to, like in this fashion, vertically or horizontally. There is no diagonal connection because we are only considering 4 connectivity here. Okay, now I think they are connected to each other, and but it looks so now the problem is that our grid or graph, it looks so simple and it's very easy to find the path. Yes, it will be easier. So let's say that instead of 10 and 11, 14, we have 14 and 15, these nodes are, or we can do it here also. Yeah, so instead of 6, 7, we have these 2 nodes, they are also blocked, let's say. So we have to do a couple of more work here. The thing I'm doing it because the graph will look so simple, so it's obvious that there is only this path or this path, then it doesn't make any sense. Okay, so let's make it like this. We have these node number 5, 6, 7. Okay, node number 5, 6, 7, they are, let's say they are blocked. There we have obstacle. Okay, so now let's make it like this. It means there will be no connection to these nodes here because there is an obstacle here, but there is a connection here. So there is always horizontal or vertical connections to the neighboring nodes here. Okay, so now it looks a little bit complex. The map looks complex. So should I number them also? I think let's also number them for simplicity. So this is node number 1, this is node number 2, 3, 4, 5, we have 6, 7, 8, 9, 10, 11, and then we have 12, 13, 14, 15, and 16. So we have 16 nodes here. So this is now our graphical representation of the grid. Okay, you can see the red dots are the nodes, and you can see also the lines, they represent the edges. So now we have a graph, and we just have to, what we have to do is we just have to apply a graph search algorithm to convert to find the shortest path in the graph. Okay, so let's see how we can do it in the Matlab code. We need to remember this also, because when we have to make the adjacency matrix, we need to know which nodes are connected to other nodes. Okay, so let's start with our Matlab. Let's first define the nodes you have. Define coordinates of nodes. So nodes, we create a variable called nodes, and no, it's not variable, it's actually an array, and in this array we define the coordinates of the nodes. So our first node was the x component was 1 and 1, and then we have the second node had the x component of 2 and y component of 1, and the third node had x component of 3, y component of 1, and the fourth node is like this, 4, 1. Okay, and then we have our fifth node had an x component of 1 and y component of 2. So this is how I look here. So this is our node, and if you see here, this is the x component, x-axis, and this is y-axis. So this, our first node, has if you see its x and y coordinates, it has x coordinate of 1 and y also 1. The second node here, the second node has a x coordinate of 2, but y coordinate is again 1. And similarly, third node has x coordinate of 3 and y coordinate 1. Then if you move to the fifth node, it has an x coordinate of 1 and y coordinate of 2. So you have to take it, keep it in mind, this thing. And when you are programming in Matlab, you have to think about this picture. From here you can have an idea about the node numbers, and from here you will get an idea about the coordinates of these nodes. Okay, so let's go back to Matlab, and we were on our fifth node, and then we go to our sixth node. So for the sixth node we have x component 2, y component 2, and for seventh node we have the x component is 3, y component is 2, and then we have 4 and 2. How many nodes we have here? 1, 2, 3, 4. 1, 2, 3, 4. You see that there's a trend here. So 1, 2, 3, 4 x changes like this, and then y is 1, 1, 1, and so we can use it like here. One, 2, 3, 4. And just copy paste it to make it quicker. Okay, so this was the first row, this was the second row here, and then we make the third row now, and here will come only 3 and 3, 3 and 3. So this is our third row, and now we go to our fourth and last row. This will be 4, 4, 4 and 4, and then bracket close. So this is how we define the coordinates of our nodes. You remember that if you look here in the previous lab, we did the same thing. We first defined the coordinates of our nodes in the graph, where they are located. Okay, so this time it's same, we did the same, but this time we have more number of nodes, 16 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so this space here, it's not necessary. I just gave it to simply for visualization, for easier visualization. Okay, once we have nodes, now we have to define the adjacency matrix. Okay, so our A matrix is equal to, here you need to know what is the connectivity between the nodes. Okay, so if we look at it again here, let's try to make a matrix here. Okay, the adjacency matrix. So you remember what the adjacency matrix tells us about the connections between the nodes. So if we see the adjacency matrix of this graph, then we say that, okay, our A matrix is so here we have the rows and columns here. Okay, so we say that node 1, let's imagine we have here 4 nodes, node 1, node 2, node 3, node 4. Or let me make it easier. We call it, okay, this is node 1, node 2, node 3, and node 4. And similarly, in this way also we define node 1, node 2, node 3, node 4. Okay, so now this is our A matrix. We call it like A. Okay, so is there any connection between node 1 and node 1? No. So we put it here 0 here. Is there any connection between node 1 and node 2? Node 1 and node 2 here. I think it's wrong. It's not correct. I just realized that this matrix this should be, to represent this graph, this matrix should be a size of 16 by 16. Okay, so 16 rows and 16 columns. So this is, and which is difficult manually to do that. It will be much more difficult. Okay, if it's a small one like 5 by 5, we did it in the previous graph-based pathfinding, then it will be easier. But for this particular example, we need to find another method. This manually making the adjacency matrix, it will be too time consuming. It will be so big also. So what my idea is that let's make a matrix of 16 by 16, and A is a matrix 16 cross 16, and because it shows the connectivity between different nodes. If you remember that, for example, in this let's see a small example, or it has something like this here. So 1 1 0 1. So here, for example, here it shows that, you imagine here node, this is n1 row, n2, and this is n1 column and n2. So let me write down here. This is A matrix, and imagine that this is n1 here, and this is n2, and similarly here n1 and n2. So how it works, the adjacency matrix, it shows that if n1 and n1 are connected, so it means there should be 1. But normally same nodes are not connected, so it should be 0 here. Okay, and if n1 and n2 are connected, it means it should be 1. So here you see n1 and n2 are connected by an edge, so we put here 1. Okay, but n1 and n1 are not connected, so we put here 0. Similarly, n2 and n1 are connected. Okay, so n2 and n1 are connected, it means it should be 1. So it depends upon you if you want to make a directional graph or unidirectional graph. If you want to make it unidirectional graph, then you have to also put it here 1. I put it 1 here, it means n2 and n1 are connected in another way also, from n2 to n1 also. And if you look, n2 and n2 are connected, so we make it 0 also. So this is adjacency matrix on a small level for only 2 node level. Okay, but for the complete representation we need a 16 by 16 matrix. So to avoid this, what we do, we shall make a 16 by 16 matrix in Matlab, and then fill them with all ones, so there will be fully connectivity between all the nodes. And then we manually remove connectivity between some of the points. For example, we say that there is no connection between 1 to 5 and 2 to 6 and 3 to 7. Okay, so this we have to do that. And also there is no connectivity between 5 to 9, 5 to 10, and 7 to 11. So this we here write down here. Okay, so 1 to 5, there is no connectivity, and then we have 2 to 6, there is no connectivity here, and then 3 to 7. there is no connectivity. And similarly from 5 to 9, there is no connection. 6 to 10, there is no connection. 7 to 11. We need to remember it while we are manually changing the values of your adjacency matrix to 0. Okay, so let's start it. So instead of manually making the adjacency matrix, we say, okay, fill the A matrix with 1s, and 1 should be the size of nodes, and because it's a square matrix, so I think this will work. Yeah. So we have 1, 2, 3. Yes, I have to put one more here. Okay, so what this command does is it fill a matrix A with all 1s. Let me show you here, maybe in the command window. If we type down here and press enter. Okay, nodes, we need size of the nodes. Let's say nodes is equal to 16, and now we type this command again. So we have now the A matrix. Oh, why only 1? So let's try without this thing here. It means there is only one column. Still the A is 1. Okay, let's break down it, not use it in a single command, but let's break down it. Let's say n is equal to, we have size of nodes. So this is our n we have. So where we started, we want to fill A with 16. Okay, so A is equal to, what's this, 16 comma 16. I didn't forget 1s. Here you can see we have 16 by 16 matrix, and here you can this matrix, it shows a complete connectivity between all the nodes, but we know that to represent obstacles, we need to break connectivity in some of the nodes. For example, there was no connectivity between the first and the 5th node. So first and fifth node, we need to put it here 0. So it means that this element of the first row and the fifth column, it must be 0 here. Okay, so the trick is that we first make this matrix and then we manually put here zeros on the specified locations to represent the obstacles or the missing edges. Okay, so yes, so I close it here, and now let's define the A matrix. A is equal to ones, which is size of nodes and comma size so this command will make the adjacency matrix of size nodes, whatever nodes you have here. It will make the equal size of square matrix. Okay. Okay, so once we have this matrix, now we need to remove some of the elements of, or make some of the elements of the adjacency matrix 0. You can say represent obstacles in the so how we do that, we say that, okay, A. So what was it exactly? There was no connection between first node and it was fifth node. So we make 1 and 5 entry is equal to 0. To quickly test it whether it works or not, or whether we are doing correctly, just type this command here, and so we made A15 is equal to 0. Let's see it works or not. See here, it became 0. So this edge doesn't exist, so there is no connection now between 1 and 5. Okay. Actually, what I realized just now is that there are more connections between the nodes than there are not connections. But in reality, if you see that, if we look again our adjacency or the graph we look, you see that there are less connections between the nodes instead of the missing connections. Let's say, for example, if you take the full connectivity, it means that node 1 is connected with 9, with 13, 14, 15, each and every node are connected with each other. But in this particular case, there are less connections. Okay, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Only 15 edges are there. But our adjacency matrix is 16 by 16. Okay, and so it means that it's smarter if we only define 1 values in the adjacency matrix. So instead of defining the missing connections, we only define the connections that are present. Okay, let me explain it. So here we filled it with ones, which is actually, it will be too time consuming to put zeros here because most of nodes are not connected. Only 15 nodes are connected. So what we do, we fill 15 nodes actually. Okay, so instead of putting here zeros, we put 1 here. So what we do here, we make here zeros. Okay, same is here, we put it here like A, instead of 1s we put it here zeros. Okay, now our A is filled with zeros. So now we have to, in this 16 by 16 matrix, we have to put only 15 1. Okay, so let's see where we have to put it. So there is a connection between, I remember from the diagram, so there is a connection between 1 and 2, 2 and 3, 3 and 4. So let's fill them. So node number 1 and 2, there we put them here 1, and we have to put, like, do it 15 times, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You can also use for loop also, but for basic level of understanding, we shall start with like manually doing things. But later we shall use for loops and some automatic filling things. Okay. So node number 1 and 2, they are connected, and then we have node number 2 and 3, they are connected, and then 3 and 4 are connected, and then we have node number, you see here, 4 and 8, 8 and 12, they are connected, 4 and 8 and 8 and 12. Four and 8, 8 and 12, there's a connection, and then 12 is connected to 12 is connected to 11. Just wait a moment. Okay, 12 is connected to 11, and 12 is also connected to 16, and then we have 11 is connected to 10, 11 is also connected to 15, and then we have node number 10 is connected to 14, and node number 10 is also connected to node number 9. Okay. And then we have node number 9, which is connected to node number 13, and then node number 13 is connected to node number 14, and similarly we have node number 14 is connected to node number 15, and so that's how I think we are missing 2 of the entries. It seems like 14 is connected to 15, 13 to 14, and 9 to 13, 10 to 14. Yes, we have already did 10 to 14, and 11 to 15 also. So which of 2 are missing? 1 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Seems like 1 is. So yes, we are missing here 15 to 16 we have. Okay, so yes, so these are the entries, these are the edges in the adjacency matrix that we need to manually fix. So just copy paste here. So now when we look our adjacency matrix, see that most of them are now zeros, but we have connectivity between first and second node. Here is a 1 here, and there is a connectivity between second and third node here, and then we have a connectivity between third and fourth node here, okay, and so on. We have other connectivities also according to our graph. Okay, once we have defined these all connectivities, instead of obstacles we define here, we represent the edges in the adjacency matrix. Okay, so once we have defined the adjacency matrix, and now it's time to define the cost matrix. So for in our case, we make cost matrices. Let's say all of them have same costs. So we define ones, size of nodes, and size of here also we have defined the C matrix and we filled it with ones. Okay, now we have C matrix, we have the A matrix. Now we have to define the start and the target node like we did it here in the graph search. So in our case we say that, okay, our start node is node number 1, and then we have a goal node which is node number, let's say it is 9. So yes, now it's time to call the first commented here, define start and target node. Now we shall use Dijkstra's algorithm to search our goal in this graph that we have created, and also give us the shortest path. So let's see, it was here distance, and we had distance and the path. And here we have to give the start node, sorry, the A matrix here, and then we have to give the C matrix, and then we have to give the start node here, and finally the goal node. Okay, once we have a path here, then we can, why there is an error, best practice to separate output variables with commas. Okay, there's a comma here. Okay, now it seems like there is no error here, and this here, D should be smaller. Okay, so next we have to take the transpose of this path. And this is because it looks like it will be then same, it looks like what we have here, the nodes here, because here we have only 2 columns and there are like 16 rows here, but the output of Dijkstra, it will be 2 rows and more columns. So that's why we have to take a transpose, so that our path looks like our previous format. Okay, after taking the transpose, we have a path, but they are the nodes numbers, they are not the actual nodes. So to get the actual nodes from the path, we can use a for loop like we did here in the previous lab. Here we use a for loop to get the actual coordinates of the nodes. So what we do, we can just from here, to save time, we can copy paste from here. This is from the previous lab. Gplot, we don't need gplot because this is not a graph. Gplot is for plotting the graph. And we have a path xy here. Okay, we shall plot it here, and also we need something to plot our grid also now. So you remember also in the first or the second, it was first or second lab, we learned how to make an occupancy grid map, and there also we learned that how to plot a grid also. So here, as you can see here, where the plotting starts here. Okay, so from here we can copy these 2 commands, which will help us in our algorithm to make a grid. Okay, so let's copy paste them here, and then we also need to make an obstacle, which we can use either this patch command, or there is also an alternative command for that. I shall show you. For example, here you can, this command here, you can make a new figure. I hope that from here till here you have understood the basic concept. So Dijkstra gave us the path, and we took a transpose of this path, and then actually in this path there were nodes, actually number of nodes, and you have to extract the coordinates of the nodes using this for loop. And then to plot it, you have to just type your figure, and then you have to type grid on, and then hold on, because you have to type multiple things here, and then you have to type here this plot your path on this thing, the path, actual coordinates of this path. And then you have to make the obstacle, you have to write down this command here. It's called h is equal to fill and then bracket, and then you have to give the coordinates of your obstacle. If you remember from our this from here, if you remember the so here we said that here we have obstacle at node number 5, 6 and 7. So it will start from, actually it starts from 1 and it goes till 3 nodes. So from 1 to 3 it will here. So the coordinates of this will be first we have to write the x coordinates of the 4 points of the square object or the rectangular object. For example, the 4 coordinates will be here. This will be x coordinate will be 1, and then x, this is a second corner and its x coordinate will be 3, or 1, 2, 3, 4. Yeah, 4 actually, sorry, 4. So this is the first point, this is the second point here, this is the third point, and this is the fourth point here. So this area is represented by obstacle. Sorry for this confusion. This color I didn't fill it. It came from the software. I just wanted to make things better, but it seems like it didn't help. So to draw a black figure, we need 4 corners of the rectangle, and this is the first corner. Its x-axis is 1, and here this has x-axis of 4, x-axis 4, and again 1. So, and similarly their y-axis will be here it will be 2, and here it will be 2, and here it will be 3, and then again 3. So now let's try to enter it here. So here first the x-axis, what was it? 1, 4, 4, 1, and now the y-axis, it was 2, 2, and 3, and 3. And then you have to define the color, which is black we want to plot, and then close the bracket. It shows arrow here. I think, yeah, here is a mistake. So then you have to type this command. It's called h face alpha is equal to, let's say, give it a value 0.5 and then semicolon. Okay, so here we have, now we have the this will draw the obstacle here. Let's comment it also. Plot the path, and then here plot the obstacle. And then we have to set this command, the grid distance, the size of your cell should be 1 along x-axis and y-axis. And then you have to define start and the ending, not ending of axis. So for that we need x max and y max. It should start from 1 and y-axis starts from 1 also. And x max and y max we haven't defined it. We can define it here. X max is the maximum value of your grid. Let's say it's 5, and y max is equal to 5 also. Okay, so looks fine to me. Let's try to run it. Close other and just try to run this one. So here we have the path. As you see that it's on the exactly on the coordinates. It should be in the middle of the cell. Then it looks more appropriate. So to make it middle, what we do here, we just go to this plot the path and add here 0.5 to the x-axis also, and 0.5 to each point of the y-axis also, and then we plot it again here. So yes, so now you see that it looks nicer. So this is the shortest path. If you remember, we have given this is the first node, this is our 9th node, and now the Dijkstra's algorithm has calculated the shortest path in this grid. So here was our grid here, if you remember. And so yeah, so this was our grid, and we said that here we have obstacle, and so these node number 5, 6, 7, they are not allowed to visit. Okay, and then the path from 1 to 9, from our eye it looks like this is the only possible shortest path. Okay, but for computer you have to tell them how to do that. So Dijkstra's algorithm have successfully found the shortest path in the graph, and this is the shortest path. As you can see that here, this is node number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 nodes here, and this is our final path we have here. Let's try to change the final goal location. Instead of 9, let's try to give it like maybe 10, 11, 12, 13, 14, 15. Let's try to give 15 and see what happens. So where was the goal node here? So I would say that goal node is 15. Okay, so this time it gave us a weird path. I don't know why. Maybe we haven't added the clear variables, so it's not clearing the variables. Okay, so it's remembering the previous variables because we forgot to define here, right here, clear all variables. Maybe this will help. Yes, so see that now. So previously when we don't add this clear variables, so it was just remembering the previous results also in the graph and then trying to mix all of them. So this is now the shortest path from node number 1 to node number 15. Okay, so if you want to make it like more beautiful also, then you can add here, like first thing you can do is to add maybe more dark color to this face alpha. So now it's like showing gray, and if you put it 1 here, then it will give you like full dark color like this. And what else you can do here to represent your start and target point, you can give them different colors. For that you need to define here with your plot, you need to define again the plot the start and your target locations. Okay, How you can do that? You can just type this command scatter, and then you have to give the coordinates of your start and target. So I give here the coordinates like start, what was the name of this thing, start node, where we have defined it, yes, start node and goal node. Start node and it's I think start node has two or we can just I think go to our previous lab where we have written it and just copy paste from here. Where was scatter? Yeah, this was a command here for scatter. So it was scatter, and then we have start node, and its X component of the start node. Because we need the X and Y coordinates of the points, so that's why we are doing this start node and by its y-axis, so comma 2 here. So this will extract the X coordinate of the start node, and this will select the Y coordinate of the start node. And start node should be, let's make it green, and let's try to run this algorithm now. Yes, but it's here, it should be at this point, so let's try to make it. Here we have to add plus 0.5 and also plus 0.5. And similarly, we have to do this for the goal node also. Just copy paste here, and just we have to change here goal node. Okay, the color make it blue. Okay, so this is our final version of the path. If you remember, so this was our grid here. We started with this grid here, and what we did, we know that we know one algorithm, it's called Dijkstra's algorithm, that can find shortest path in the graph. It can search the goal, it can also find the shortest path. So we had a grid. Grid is just we said it's a combination of nodes and edges. So that's how we converted it into a graph. And then we said, okay, there are obstacles in some places. We said, okay, in these three nodes, in these three cells, we have obstacles. So we said, okay, they are not connected. And then we made adjacency matrix from this graph. It was a manual one, custom one. And then we define, okay, which nodes are connected. And we manually did that. And after that, we use Dijkstra's algorithm to find the shortest path between. First, we did from 1 to 9, and then 1 to 15. And this is the results. You can see that this is the shortest possible path from node 1 to node 15. This is done when we consider 4 connectivity. But if we consider like 8 connectivity, then this is the shortest path from here to straight, okay, then here straight, and then here straight to goal. Like this is the shortest path from this node. So this is not the shortest path. But if we consider 4 connectivity, then this is the shortest path. What else? Yes, so here just ignore these black cells. There are 3 black cells here. This is the thing. And so this is our result. Just see it last time. And you see that we added 0.5 value to represent them. And yeah, so this is our code. And let's see now the adjacency matrix, what we have here. You see most of them are zeros because most of nodes are not connected to each other. And there are, at some places there are ones, and these places we have manually placed ones. We said that, okay, there is a connection between this node and this node. So yes, we have defined the adjacency matrix. And then we have a cost matrix. In cost matrix, we said, okay, the cost for traveling from one node to another node is 1. And this we said all of them is 1. Then we have calculated the shortest path, but what is the distance of this? The total distance from start to goal. The total distance is 7. If it's in meters, then it is 7 meters from node 1 to node 15. And then we have, so this is a path by Dijkstra's algorithm. You see that it says that go to node 1, then node 2, then node 3, then node 4, then node 8, 12, 11, and 15. And this is the actual coordinates of the path. So first, node 1 has the coordinates of 1, 1. Node 2 has the coordinates of 2 and 1. Node 3 has the coordinates of 3 and 1, and similarly. Yes, so I think that now this is clear. And if you have any questions, you can contact me online, and I hope that we can solve your problems. So here we define the maximum size. Here we define the nodes, actually their coordinates, which you have in the grid. And then we have, here we define the adjacency matrix. And then we manually, in this adjacency matrix, we manually define where the edges are located, which nodes are connected to each other. So this is how we did that. we just in the adjacency matrix we said that okay, node number 10 and 9 is equal to 1, means they are connected. And then we define the cost matrix, which is just, we said that okay, all the nodes or all the cells in your matrix, sorry, or in the grid, they all have same value, same cost, same distance, which is 1. And then we define the start and the goal node, and then we use Dijkstra's algorithm. This algorithm I already mentioned in the previous lab that we have downloaded from Matlab website, and in the previous lab we have also mentioned the link from where you can download this algorithm. And then we took a transpose of this path, and then we extracted the x and y coordinates of the nodes, and then finally we plotted our path here. This was our path, and then we plotted the obstacle, and then we plotted the start and goal points, and then we did some settings for the grid. So yes, so we shall end here our lab session. Thank you very much for staying with me. I hope that you have learned about the grid-based path planning using Dijkstra's algorithm. If you have any questions, I shall be available tomorrow on Google Meetings, so you can ask.